question? No big deal. Yeah, Mackenzie?
Can you do number 2, the second question? On homework 4.
The how long part?
Yes.
Okay. Well, we're gonna, just like we did in the previous one, we're just going to find the intersection. So our model would have 1 million on it, is what we're looking to get to. And we had 100 times 100 times e to the 0.2276 times x. And let's see. So this is per hour, so I don't know, 100 hours, I guess. That seems okay with the window. So there's my 1 million. There's my intersection. So second trace, intersect, enter, enter, enter. So after about 40.5 hours, it's okay with that?
Yes.
I get what's up.
So this but like in this case
Right.
so
Maybe the first part wrong. No. There. Yes.
oh I see.
Okay. And that could all work out.
Okay. And for this one, I don't know if it's like first, like for the
It always goes small to big. So the number's always smaller to bigger.
okay. Thank you.
Maddie,
Can you do number 3, the second part?
sure. What did you write for part A?
Oh no, I mean the first part. Sorry, that's what I meant.
Okay. So what's R?
That's
That's the big question, right?
would it be 25,000? Oh,
5.
okay.
So you just have that like y is equal to 100 e to the 0.5 t.
Oh, okay.
So you're just plugging in 25,000 for t. I guess I forgot years there. But that's it. Okay. So today we are going to introduce a new concept, quite an important one, as it'll be kind of the focus of our second half of this chapter. So we know like 2 to the second is 4, and we know 2 to the third is 8, right? But what power of 2 gives us 6? Do this. So what can we say about that number there? If you were to take a guess, what power of 2 gives us 6?
2.5.
2.5. Not unreasonable guess, right? 6 is halfway between 4 and 8. 2.5 is halfway between 2 and 3. Right? Not quite enough. So what do you want to try now? Should it be more than 2.5 or less? More, okay.
7.
2.7, okay. Oh, too much. Okay, let's try another one. What do you want to do now? 1.6, that's fine. Still too much, but just a little too much. What do you want to do now? 5.8, okay. Not quite enough. Needs a little more.
5.9.
Try 5.9. Still too much. Okay, 2.585. Getting closer, still a little bit too much. So we can keep playing this game with this number in the decimal, right? Where we're going to get closer and closer and closer. You know, kind of going up and down and up and down. Well, how many decimals do you think that number is going to be? That one in the exponent.
A lot.
A lot. Can we be any more specific than a lot? What? Infinite. Do you think there's going to be a pattern?
Something repeating kind of thing?
Do you think it's going to give a repeating pattern in that number in the exponent? What do you guys think? Probably not, right? What do we call that kind of a number? Irrational. Everybody agree with that? So we're going to give a number, we're going to give this specific number a name to represent it, because we don't want to write down an irrational number, just like we gave 1.414 yada 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 the name square root of 2, or the number 1.69 yada 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 the square root of, or the square root of 3. We're going to give this number a name also. Everybody okay with that? So this number, question mark in our case, is going to be, we're going to call log base 2 of 6. So this tells me 2 to the question mark power is 6. So basically this is saying, what power of 2 gives me 6? That's the number that we're representing there. Power of 2 that gives 6. Everybody okay with that? So this is just a name, right? Like the square root of 2 is the name for a number, the square root of 3 is the name for a number, or pi is the name for a number. Log base 2 of 6. It's just a name for a number. Specifically, it's describing the exponent of 2, the power of 2, that equals 6. Are you okay with that idea? So what if we wanted to know the power of 3 that gives 10? How would we write that? Log base 3 of 10. Everybody okay there? So in general, what we're going to say is y equals b to the x is equivalent to x equals log base b of y. This is what we use to define a logarithm. Okay. So again, this logarithm is just describing the power of some number, or what power of a base is equal to some number, right? So we can use this definition to evaluate logarithms. So for example, if I did log base 3 of 81, I can evaluate that. So if I think about this as the equation x equals log base 3 of 81, what I'm looking for is the power of 3 that gives me 81. Does anybody know that off the top of their head? It's a common one we probably encountered several times in the previous chapter. It's 4. Yeah. 3 times 3 is 9. 9 times 9 is 81. So that's 4 3's multiplied together, right? Everybody okay there? Now, when the logarithm is a whole number like that, this is fairly routine, right? Not too tricky. We can come up with some tricky ones to just to still have like rational numbers. What if we have, say, log base 2 of 1? Let's do something that's maybe a little less obvious. 1/4. So Again, what is this saying? It's the power of 2 that gives us 1/4. So I would, again, here let's be a little bit more explicit with what we did. In the previous problem, we just kind of asked and somebody knew the answer on site. My goal here is to rewrite 1/4 as a power of 2. Everybody okay with that notion? So I know that 1/4 is just 1/2 squared, right? And I know that if I have a reciprocal like that, or I can make something a reciprocal by using a negative exponent. You guys remember that property from last chapter? So here, x is -2. Since I know 1/4 is the same thing as 2 to the -2, the power of 2 that gives me 1/4 is -2. And you can always check that in your calculator. Is that okay with you guys? What if we did log base 4 of 2? So here, what power of 4 is equal to 2? Now, can I rewrite 2 to get 4? No. But can I rewrite 4 to have a base of 2? I can do that. So let's do that instead. Right? 4 is just 2 squared, right? And if I have an exponent of an exponent like that, they multiply. So for these two to be equal, since their bases are equal, I would need their exponents to be equal, right? You guys agree with that? If that equation is equal, it means the exponents also have to be equal. So that tells me the x is 1/2. Which should make sense, right? The square root of 4 is the same thing as 4 to the 1/2, and that's just 2. So just to kind of show you how to kind of manipulate these. Now, I want to point out to you that your calculator can handle this stuff as well. So if you take a look at your graphing calculator, if you look in the math button, and you look at down at the bottom of the math menu tab, you'll see a command called log base. And there I could just type in my base for my logarithm and my argument for my logarithm and press enter, and the calculator will spit out the exact answer, which is nice. Although the exact ones we can technically do by hand, they're not that bad. But if we wanted to do something like log base 2 of 6 that we started off talking about, that's one where there is no exact answer to it. This would be one we'd have to use the calculator to, or we would use the calculator to evaluate. And we get that long irrational number, right?
What would we, for the decimal, what would we stop writing at, like the hundredths place?
Whatever I tell you to round to
Okay.
in the direction, if it's something where I expect you to get a decimal answer. How are we doing? So far okay? So, to this point, when we've talked about operations in mathematics, we've often talked about them in inverse pairs, right? So like the first operation you guys would have talked about was addition. And shortly after addition, you talk about subtraction because we use subtraction to undo addition, right? They are opposite operations, or inverse operations, I should say. After multiplication, or after addition, subtraction, we talk about multiplication. And shortly after that, you can start talking about division because we know that division undoes multiplication. Again, those are inverse operations, right? Everybody okay so far? Next, we would talk about exponents. So like something squared. And we know that to cancel that out, well, I'll just be general and say that. We use a nth root, right? But those things are inverse operations of each other. Everybody's okay with that? And now we've reached a place where we have a new pair of inverses. So if I have exponent base, its inverse is log of the same base. So for example, if I did log base 2 of 2 to the third, that should just be 3. Because the log base 2 would cancel the exponent base 2. Similarly, if I had 2 to the log base 2 of 3, that would also equal 3. Because the exponent base 2 would cancel with the log base 2, leaving me with just 3. Let's just kind of verify that notion on our calculator, because these are things we can do on our calculator. Just as a little bit of practice using the logarithms again. So I'll do log base of 2 to the third. That gives me 3. And then if I do 2 to the power log base 2 of 3, I also get 3. It didn't lie, you guys. Everybody okay with this notion so far? So since these two operations are inverses, we can use them to find like inverse functions. So let's say we have this exponential function, y equals 2 to the x plus 3 minus 5. And we want to find the inverse for this function. Remember the procedure for finding an inverse. We want to isolate the x, and then we swap the x and y variables, right? So first thing I would do is I would add 5 to both sides, right? I would assume that most of us would think to do that first. Then we need to cancel that exponent base of 2 to get at the x, right? What do I need to do to cancel that exponent base of 2? Use a logarithm. Which logarithm should I use? The same logarithm, or the log with the same base as my exponential. So in this case, I would do log base 2 to both sides. Everybody okay to hear? And as we just got done discussing, the log base 2 will cancel the exponent base 2. So on the right-hand side, we're left with just the x plus 3. And then all we have to do to finish this problem out is to subtract 3 from both sides and then swap my variables. When I subtract 3 from both sides, where is that 3 going to be subtracted from? Can I subtract that 3 from the 5? Definitely not. Why not? Because that 5 is inside the logarithm parentheses, right? You can't just subtract the 3 willy-nilly inside of there. So where's that minus 3 going to go?
On that side?
Yeah, just tacked on to the end. Exactly right. And then when we swap our variables, there's my inverse. Let's just kind of verify that visually, right? I know when I look at the graph of a function and its inverse, they should look like they're reflections across the line y equals x. So let's just kind of do that. There's the original. There's the new one. And I'm going to include the line y equals x also, just so we can see that. We'll just do like, we'll just take the standard window there. So I'm just going to do zoom standard. So here's my exponential. Here's my logarithmic. And there's my line y equals x. And let's turn the axis off. It'll be easier to see what's going on here. So again, here's my exponential. Here's my logarithmic. And there's my line y equals x. For whatever reason, my calculator isn't drawing the entire logarithmic. This should continue going. It has to do with that vertical asymptote there, and I guess what's going on. I don't know why that's being weird, but as you can see there, they look very symmetric across that line y equals x, right? Which is what we'd expect to see from inverse functions. So, do we feel okay doing that? So we've established this new operation called a logarithm that describes the exponent for a base and what it would be equal to. So like what power of 2 gave me 6. That's kind of what we mean by a logarithm. We talked about how to evaluate these logarithms by hand, just using the definition and some of our properties of exponents and stuff to evaluate those. We talked about how we type them into our calculator. We talked about the inverse relationship between the exponent base and the logarithm and kind of how to use those two to find an inverse function. Let's go the other way, though, just for grins. Let's say we have a logarithmic function. And let's say we want to find the inverse for this. So again, same idea. We want to isolate the x, and then we'll swap the x and y variables. First thing I would do is, add 5 to both sides. Very good. And then to get at the x, we have to get rid of that log base 3. So what is going to get rid of the log base 3? Ready for your hint?
Would we take the 3 and put it in front of the logarithm?
So it's an exponent base of 3. Yeah, so we have like big 3, because we're not multiplying. The 3 is the base of an exponential. So I'm going to write this like exaggeratedly big 3. So if you're going back and you're looking at this, you know that we're not multiplying by 3. Right? Is everybody okay with that? It's a common mistake I see students make. But there's no multiplication going on here. It's an exponent base, which is very different. So that exponent base 3 cancels the log base 3. So we have 3 to the y plus 5 equals, we just have the x plus 4 left. And then we subtract 4 and swap to get this. Everybody's okay with me doing that all in one step, I hope.
I think it's a 1, not a 4.
No, that's what I thought
Oh.
it was.
Yeah, I just copied it. My penmanship was too bad that I couldn't read my own writing. Never happened to you guys? Happened to me. Thank you. Appreciate that. Probably makes a lot more sense that it didn't become a 4 all of a sudden, huh? I'm glad that somebody was able to reason that, like, yeah, you just read the number wrong. Oh.
When you bring it over, do you just just bring it up?
You see it? Okay. Yeah, it works exactly like you'd expect, right? You can't subtract it to the exponent.
So the 3 with the y plus with the now x plus 5 is now the base of that. I like that part. So it's like the 3 is the base and then the x plus 5 is the exponent.
Correct.
Okay.
Yes. Yep. That's exactly what's happening. Does that feel okay? Going the other direction, working very much the same way, where we're using exponent base and logarithm to cancel each other out. All right. A little logarithm notation. There are 2 special logarithms. The first one is called the Common Logarithm. And that is log base 10. But we don't write log base 10, we just write log with no base there. If you look at your graphing calculator, and you look at the left-hand column, you'll see the LOG button. That is the log base 10 button. Everybody located that? The second special logarithm is the natural logarithm. That is log base E. But we don't write log base E. We write ln. So I find that, again, when writing logs, I like to use cursive. My penmanship isn't great, and I've seen many students take a log and turn it into a 10G when they're writing printing, and I've seen them take ln and turn it into 1n when printing. I like to use cursive because I refuse to make those mistakes when I'm writing it in cursive. I've never done it with cursive. The students that write cursive never make that mistake. I would encourage you to, even if you don't really write in cursive ever, don't know how to write in cursive, we're just talking about like 4 letters to write in cursive, L, O, G, and N. I think you can probably handle that much. But I'd strongly recommend using cursive to kind of draw those. So it's just abbreviations, right? Log base 10 is just log. Log base E is just ln. So again, it's nothing more than like an abbreviation. Why? It's because those are the ones that we've used the most, and so it saves us a couple of symbols because mathematicians are supremely lazy about stuff like that and want to use abbreviations whenever possible. One last idea and we'll call it a quit. Sound good? So we've introduced this new operation called a logarithm, right? What we need to do now is talk about how we can kind of manipulate logarithms, right? So there are 4 special properties that describe to you how we can kind of manipulate a logarithm. So the first one is the product property that says the logarithm of x plus y is equal to the logarithm of x plus the logarithm of y. And this is a multiplication symbol. I know that kind of didn't look very dotty there. It's supposed to be a dot. Multiplication. Now, who thinks that's kind of odd? That multiplication inside the logarithm becomes addition outside the logarithm? Well, if you think about it for a moment, it's exactly the opposite of how we multiply exponentials, right? If you multiply, multiplication outside of the exponential turns into addition inside the exponential, right? And we know that logs and exponentials are inverses, so the reverse is happening. The multiplication inside the logarithm turns into addition outside the logarithm. Isn't that kind of neat? If we were to prove this product property of logarithms, we would use this property of exponents to do so. Because we rewrite the logarithms as exponentials, apply that property, take the result and rewrite it as a logarithm, and you'd be done. Next we have the quotient property. That says the logarithm of a quotient is equal to the difference of the logarithms. Important point to make here, the order in which you write log x and log y definitely matters. The denominator needs to be the logarithm that's negative. Everybody's okay with that? Again, that's fairly obvious, but I want to point out that that definitely matters. Most of us go ahead and apply the property without ever thinking to want to change things around. Some of us are contrarians and want to be able to know if I can change things around or not. Here you definitely cannot. It has to be, the denominator must be the negative logarithm. And our next one is the power property. And again, the power property looks kind of weird at first glance, but if you think about it, that's exactly what we're using when we're simplifying a logarithm. So we say, log base 2 of 2 to the third was just 3, right? Well, this is the same thing as saying 3 times log base 2 of 2 to the first, which is just 3 times 1, or 3. So again, that's the power property happening, whether you're thinking about using it or not. That's just kind of an aside there. Again, some of these properties look kind of strange. I just want to connect them to you. This one, the power property, FYI, is basically equivalent to that exponent of an exponent property. That's the one you'd use in order to prove that. It's a little bit more difficult because of the exponent of an exponent situation going on there, but it's not too bad. And then, oops, I did 1, 2, and then 4. Can you tell I was up all night? My daughter did not want to go to bed. It was lots of fun. The last one is called the change of base formula. And this one is not so relevant for you guys because your calculators have this log base button built into them. Back when I did this, our calculators did not have a log base button built into them where you could put in a log of any base. We use this formula to do things like log base 2 of 6. So log base b of a is equal to log base c of a over log base c of b, where c, that value c, is a number of your choice. So when I was in high school, the choice you'd make was either 10 or e, so you could use the regular log, the common log, or the natural log that was built into your standard scientific calculator, even though the log of any base wasn't an option on your calculator. Doing this now for you guys isn't really super useful because you have that log base button that I showed you where you can just type in whatever and they'll give you the value. And the calculator handles it for you. But this is what we had to do back in the day. It's still a good thing to come across here and there. So just FYI to illustrate this. So if I wanted to do log base 2 of 6. We've beaten this horse into the ground pretty good today, but it's that, which would be the same thing as log of 6 divided by log of 2. Or I could do the natural log of 6 divided by the natural log of 2. Or you could pick some other log base if you wanted to. Every once in a while you get some crummy algebra problem, like some solvent problem, where using the change of base formula might be advantageous to you. That happens in calculus every now and then, where it's like, oh, look, if I do the change of base formula, I can do this and this and cancel these things out. Turn this into something that's a lot simpler to deal with. But not something that we use a lot here. And then we just want to say a couple of asides real quick. So log base b of b, that's just always going to be 1, right? Log base b of 1 is going to be so b to what power is 1? This is a property. 0. Yeah. And then if I say log base b of a is defined for a's greater than 0, why would that have to be true? If I take a non-zero number and raise it to a power, can I get 0? No. Can I get a negative if I'm taking a positive number and raise it to a power? So, again, here I've snuck in this restriction on b that it's positive and not equal to 1. Where else did we see that?
Wasn't that in the last one?
Yeah, when we defined an exponential function, we said the b was positive and not equal to 1. The same idea for the logarithm base matches the exponential base. So let's just do a couple of examples now using these properties, and we'll be done for today. So there's 2 major types of problems that we'd ask you to do using these properties. So the first type is called expanding. So that's taking 1 log and writing it as like many logs. So let's
squared minus 1.
So let's say we have log of x squared y over z. Everybody's okay with what we have here? So when we talk about these properties, when we are expanding, typically we want to do quotient, then product, then power, unless you have some set of parentheses that's indicating you to do something in a different order. But that's the order in which we really want to apply those properties. So again, quotient, power, or product, then power. And if we're doing the opposite, if we're condensing, we go in the reverse order. So power, product, quotient, if we're doing the opposite type of problem. So just FYI. Let's return back to our example now. We're expanding, so the first thing we're going to look to do is look for quotient properties. So is there any division going on inside my logarithm? Yes, right? So I can apply the quotient property to say I have log of the numerator minus log of the denominator. Jeepers creepers, it's getting bad penmanship here. I'm just tired, guys, you know? You know when you're tired, your penmanship starts to go? Literally, I put my daughter to bed at like 8:30. She woke up at 10:30 and really didn't go back to sleep until about 2. So it was a fun night. Anyways, continuing on, the next thing we check for is product property. Do we see any multiplication going on inside the logarithm? In the first logarithm we do, right? We have x squared times y. Everybody agree? So I can apply my product property there. And then nothing on that last logarithm, right? It's just going to stay the same. Everybody okay with that? And the last thing I'll do is look for power properties. Do we see any power properties? Sure, in the first logarithm. So the power property just says to move the exponent to a coefficient. And the other ones are just going to stay the same. And I'm done. That's expanded. You might say, why in God's name would you ever want to do that? And you'll answer that question if you take the calculus course, because if you're taking the derivative of the expanded version versus the original condensed version, the expanded is much easier. It's actually a technique called logarithmic differentiation, which literally makes that big of a difference in problems that are pretty complicated. It helps. So it's a technique. And we're just kind of building that foundation now. But it is something that makes other problems down the road considerably easier. Let's just do one more of these. I'm going to write one up and give you guys a minute to work on it. Okay with that?
Is it expanding?
Yeah, it's still expanding. So we'll give you guys 5 minutes or so to kind of plug through this, and then we'll go through it together. If you get stuck on it, no big deal. And then we'll talk about condensing, and we're done. Or do some condensing examples, and we're done. I know I feel like I've advertised being done a lot. But we're still in the same, like we're just talking about the last topic still. I'm just doing examples from the properties. We gotta do some example problems, right? Only do 2 examples of the 2 types. It just happened, you know. Maybe I shouldn't have advertised that we're almost done. You guys get it. Life is hard sometimes, you know. Do you guys have AP tests coming up this week?
Yeah.
Or not this week, probably next week. Is it which is history? Is it US? Is that the one that most of the sophomores have?
Mm-hmm.
Or I should say a lot of the sophomores have. That's the first AP you can take, right? Is US history, I think.
And computer.
Oh, computer science. A, right? Maybe you could be taking B, who knows? I don't know. If you're some computer math scientist or something. What day is that on?
Thursday.
Thursday next week. Is that an A day or a B? That's got to be a B day.
Yeah.
So that's. Okay. Does it overlap this class period?
It's like half of it.
Yeah, and then-
It's supposed to go to one chapter, finish things.
Okay. That's good enough. I'll know not to really plan anything for that day. You guys will probably be pretty checked out by that time anyways.
Oh, yeah.
So, it's not the end of the world. We're doing pretty good in this section, or this chapter, moving along. All right, let's see what happens here. First thing you guys should have done was the quotient property. And then you should have done the product property. This is the place where if you're going to make a mistake, the most likely mistake happens here. I'm guessing that many of us wrote this, which is incorrect. The tricky thing is, this whole logarithm is negative. So when I apply that product property, everything that it becomes also has to be negative. So like that negative sign has to distribute through. Very sneaky. It's something I'll show you a bunch of times, and we'll see it in homework, and you'll still make the mistake later on because it's so very sneaky. But I'm hoping by showing it to you a bunch of times, at least like many of us will not be tricked by me later on when I do it again. We're good with where the second negative came from. Okay. And then the last thing to do is the power property. There's actually two power properties going on here. The second power property is from the square root. What exponent is a square root the same as? A 1/2. Right? That would be the second place that I would have likely, you probably just didn't do anything with the square root would have been my guess. But you can. Remember, radicals are equivalent to exponents. We talked about that last chapter. So I'm just using that same property to move the exponent. Or turn the radical into an exponent and then move it. You don't need to write that as separate steps. You can if you want to. Or write a little note to yourself on the side or whatever floats your boat. But overall, expanding shouldn't be too bad, right? That doesn't feel too difficult. There's nothing really complicated algebraically going on there. Let's do some compressing. And compressing, I would say, is maybe the more difficult of the two problems, but not that much more difficult. Okay. So again, remember the order in which we want to apply our properties when doing compressing is the opposite. So now we're going powers first, product second, and quotient third. And we're looking, instead of at the left-hand side of our properties, we're looking at the right-hand side of our properties and going kind of the reverse direction, right? So when I look for a power property here, I'm looking for a coefficient. I see two power properties going on, right? On the second and third logarithms, the power property is going to allow me to move that that coefficient to the exponent. Everybody go to that? Next thing I'm going to do is look for product properties. So here I'm looking for things added together. I see two things that are added together. That's one product property. So that can turn into log of xy cubed. And lastly, we look for quotient properties. There I'm looking for things that are being subtracted. There is one of those. And remember, the negative part is the part that goes in the denominator. Okay, we'll give you guys one to do, and this is the last thing we'll do. We're just going to do this one and go through it, and that's it. So give this one a go. We'll go through it here in a moment. I'll scroll that up because it looks like people are bobbing their heads around trying to see, because I probably had it too low on the board. Do you like this new projector they gave me while I was gone, though? How much easier is stuff to read with this thing? It seems like it's much brighter and clearer than the other one was. You think so? I think it's an improvement. It's definitely brighter, right? This thing really kicks out some good brightness. Probably got a lot of lumens in that bulb. I think that's the unit of brightness that things are measured with, or one of them. My favorite unit of brightness, though, is candle power, which sounds like such a silly name. Like, oh, that light bulb's worth 40 candles. You know? I think that's really a funny name for a unit. Like horsepower is. You know, like, oh, this is 350 horsepower. It's like, oh, that's a whole herd of horses there, huh? What does that really mean? I'm not even really sure. Like, how much work does a horsepower do? I don't know. Is that like 3 fields? Is that what we measure horsepower in? How many fields you can do in a day, plow in a day? I'm not sure. Doesn't make any sense. Now I'm just talking to try to make jokes. They're kind of schooly jokes, so they're not that good of jokes. But all right. First things first is power properties. I see 3 powers going on, right? So x to the 1/2 is the same as the square root of x. I'm going to leave the negative signs there. If you wanted to, you could take the negatives with you and turn it into like plus log y to the -2 if you wanted to. And it's not the way I prefer to do it, but it would be okay if you wanted to do it that way. Just for the record. I usually just leave the negatives there when I do it, but it's not wrong if you wanted to take them with you and turn them into pluses. Everybody's okay with what I'm saying there? Okay. Then I'm going to look for product properties. There is a product property going on here. And you're like, no, Mr. Kulik, I don't see any addition symbols. And I would say, well, you have to squint a little bit, because I can factor a negative sign out of these last 2 logarithms. And whoa, there it is! It was hiding on you guys. Were you surprised? It snuck right up on you, didn't it? So there's really just one quotient property going on. And really, there should only be one quotient property going on, because when you write a fraction, how many denominators do you have? Just one, right? So like, if you're trying to use the quotient property more than once, you probably missed an opportunity to like factor a negative like we did here. But that's it. Now we're done.